Okay, so I want to reiterate some points of the periodic table, and that is that, remember, the vertical columns are called groups, and the horizontal rows are called periods. We learned last time that, there's this stair-step line, and the elements to the left, in this slide, they're all green. We consider those metals based on their chemical and physical properties. And up here in the upper right-hand corner, we consider those, non-metals. And then the stair-step line have intermediate properties, so they're called metalloids or semi-metals. All right, and you can see the atomic number at the top. Here's just an example of chromium, and that's the number of protons. And as you move across the periodic table, 1, 2, 3, 4, you can see we're increasing in atomic number, and you know that you're adding a proton to the nucleus as you move across the periodic table. At the same time, you're adding an electron. And as it turns out, there's the concept called electron configuration, which talks about where the electrons are in relationship to the nucleus of these various atoms, of these the atoms of these elements as we move across the periodic table. And we could spend days and days on electron configuration, but we don't really need, but in this class, we're going to give you information on this as need-to-know basis. And all you really need to know is that as you move away from the nucleus, say this is the nucleus, and I'm going to go ahead and draw this orbit model, even though this is not, how it really is, but just to make a point here. So say that's level 1, this would be level 2, this would be level 3, but really they would be spheres with, the electron can be anywhere in this sphere. Imagine an onion. An older term used to be shells even. They would call them shells, but really we prefer just to call it levels. But you'd say level 1, level 2, level 3, and you can see that the volume in space as you move out just gets bigger. And that means that we can accommodate more and more electrons as our atom gets bigger and bigger, and we add more and more levels. So as it turns out, in the first period, we're only filling electrons in the first level, so we can have up to 2 electrons in that first level. When you get to the second period of the periodic table, say lithium has 3 protons, so it has 3 electrons. So it would fill up the first level with 2, and then that third electron would be found out in the second level. And you can keep filling the second row of the periodic table, 1, 2, 3, 4, 5, 6, 7, 8, with 8 electrons until you get to neon, which has a total of 10 electrons. 2 would be in the first level, and then 8 would be in the second level. And then when you come back around to the third row of the periodic table, you'd start filling the third level. You have 11, so 2 would be in the first, 8 would be in the second, and then that number 11 would fall out into the third. And so in the last unit, we talked a little bit about the valence shell, or the valence level. That's the outer edge of your atom. The valence is the outer edge of your atom. And so in the case of hydrogen or helium, the outer edge is just going to be, where that level 1 is. In the case of the period 2 elements, the outer edge is going to be the level 2 electrons. And in the period 3, it's going to be the level 3. So you can see why we said group 1 has 1 valence electron, group 2 has 2 valence electrons, because that's the number of electrons in the outer level. And it's repetitive, it's periodic as you move across the periodic table. You swing back around, you're filling up the next energy level. You swing back around, you're filling up the next energy level. That's why all of these elements in group 1 have 1 valence electron. That's why all the elements in 2 have 2 valence electrons. Then remember, when we get to the transition metals, it gets a little bit crazy, and we're not going to go into why. It's not really necessary to know for you. So we're going to focus on just what we call the representative elements, and just worry about these 3 levels, and how, as you add electrons, they move out, and then that way we can understand a little bit better physically what's going on with this valence electron business, and we can see why this has 3 valence electrons, whether you're in group 2, period 2 or period 3, and these would all have 4 valence electrons, etc. Okay, so there's a correlation between the way that the elements behave bonding wise. Remember, the metals, when they combine with nonmetals, they're going to want to give up their valence electrons to form cations, and the nonmetals are going to pick up electrons to form anions. And together, they're going to form ionic compounds, and we were able to name those. All right. And there's some interesting things about nonmetals and nonmetals forming covalent compounds. So as it turns out, like I just said, the valence electrons help predict the bonding. Okay, and we saw that in the case of the ionic bonding. And so this chart is showing us that, just this little snapshot of the top part of the periodic table. Group 1, they've left off the transition elements because they don't follow this pattern and we don't need to deal with them. And they're just showing what we call the representative elements. And they're going up to the first 18 elements. And what you see is at the top is the atomic number, the little blue, and then at the bottom is the number of valence electrons. And you can see how within the group, the valence electrons stays constant, even as you're adding protons and electrons. Okay, so the periodic nature of the way these types of elements bond, and the reason why we can predict that, yeah, lithium is going to form a compound called lithium chloride, just like sodium is going to form a compound called sodium chloride, is because of their electronic structure, and we can infer that from the periodic table. Okay, so the periodic table, as you'll find out in the video, the elements were all organized before people understood this business about the electrons and where they were. Well, they were starting to be organized in this way, in this periodic table. And it's just amazing that the electronic structure mirrors so nicely the position on the periodic table.